So Monday at 2, Zaya Friedrich will give a talk at Big Room, at Seminar Room 1. And it will be the survey of the stuff we will be discussing. So this scatterers on non-torus, he will give a survey. And then we will actually move to this room, and people who want to discuss scatterers on torus will be sitting in this room and discussing on this board. So there will be something like 7 more people coming next week, and we will be having informal discussions. So this room will be is booked actually for entire next week for informal discussions related to these scatterers. There will be one more event. Jan-Philippe Solovey will be coming next week, and he will give a talk as well. And initially we thought we planned his talk for Tuesday, but then we have moved it for Wednesday, so Solovey will be talking at 2 o'clock on Wednesday. After all, yeah. Sorry?
Singing. Solovey, singing.
Yes, yes. Okay, at least this is what I have sent in my email to Catherine, but I hope this is what she will arrange. But now is talk by Daniel Elton, who will be talking about some modes of Dirac operator arising instead of graphene.
Okay, well, thank you very much. Thank you to the organisers for the invite to this programme. I should say up front there's a fairly limited overlap with the letters that appear in the actual programme title. There will be a small amount of periodicity and quasi-periodicity, although more of a function than an operator as such. And yeah, I just also mentioned it's joint work with Michael Levitin and Josef Olbrovich. Okay, brief overview. Very brief motivation.
Have been there?
Really? On the screen. Hang on. Screen.
Yes. Don't touch it.
Right.
Don't breathe. Then step away
Maybe
from
this is stepping on this thing.
Don't breathe.
Okay, so after giving some motivation, I want to introduce the two spectral problems. They're both non-self-adjoint, quite closely related, and basically spend the rest of the talk trying to give you some information about their spectra. So I'm trying to study the spectra of these two problems in a fairly general context, so for fairly general potentials, trying to get as much information as possible. The operators involved are quite simple. 2x2 first order system of ordinary differential operators. So the straightforward operators, nothing fancy there. The methods, largely classical. I mean, they're ODEs, so a lot of classical methods apply. That's basically how most of the results are proved. But hopefully I can persuade you that there's actually some interesting results. There's actually some remarkably subtle dependence on some of the spectral properties on these potentials. So despite a relatively simple problem, at least in this non-self-adjoint context, we can get some rather interesting behavior coming out. Okay, so the motivation, it's the problem of an operator coming out of graphene. So, as we all know, graphene is a periodic structure. It's got a hexagonal lattice in 2 dimensions. The physicists have come up with various models to describe the electronic properties of graphene. One of the simplest, you use the type binding. You can then apply block analysis, flow K analysis, I guess block in this case, given it's the physicists. The dispersion relation you get has these Dirac cones that Peter Kuchman showed us pictures of in his talk about periodic problems. And furthermore, the Fermi level, at least for graphene sitting without potentials, external potentials, sits at the tips of these cones. So in terms of mobility problems for electrons, at least at low energies, we actually want to look at the spectral properties of what happens at the tips of these cones. So we can reduce, well, with a bit of effort, we can reduce to actually a linearized problem in some sense, or not. We can look at the behavior of the dispersion relation just around the tips of the cones, which can be modeled by a Dirac operator. So the physicists have come up with a 2-dimensional massless Dirac operator that models, at least in some context, the behavior of electron propagation within sheets of graphene.
Excuse me, is this scalar particle?
Okay, so this operator here is applied to a spinner, two function. The two components represent the electron on two different sublattices of the graphene. It's not the spin of the electron. That's actually, it drops out of this model in terms of its influence. It's actually related to the two sublattices of the hexagonal lattice. But yes, the functions that we'll be working with are two component spinners. This potential that you can add on is just an electric potential. In the context of graphene, it's actually very easy to realize these things. You just put a gate on top of the graphene layer, raise the potential. A conductor or something, just raise the potential of that conductor, and you impose the potential on electric potential on the graphene layer. So potential is something that's very useful to study, and also from a practical point of view, very easy to realize. Okay, so that's the general setup. The particular problem I'm interested in is where we're looking at a potential waveguide. So in a mathematical sense, the potential U is actually just a function of one variable, which we'll choose to be the X variable, independent of the Y variable. So you can think of just taking a sheet of graphene and laying a wire across the top. If you raise the potential of the wire, insulate it from the actual graphene, you'll impose a waveguide-like potential on the graphene layer. So the potential, the V that will appear throughout the rest of the talk, is really the profile, the shape of the waveguide, the cross-section. And you want to think of V's that are local in some sense. We're trying to think of a waveguide, so the profile should decay as we move away from the waveguide. That's the kind of V's that I want to look at. Okay, well, in this particular case, it's easy enough to separate variables. So if we let K denote the wave vector or the wave number in the Y direction in this case, we can reduce two-dimensional Dirac operator to a one-dimensional one. So this is the main operator that I want to consider. If you go back to the previous page, that really should be a 1 there, and that should be a 2 there. In this context, well, it's a unitary equivalent operator. It's just a little bit more convenient to have it written in this form, but it's unitarily equivalent to the one over the page. Of course, the potential is now.
Sorry, may I just ask a question to just check whether I understand correctly? So first you looked at the periodic operator with hexagonal lattice, right?
Yeah.
Which describes it. And then you basically just were looking at what happens at near the lattice when the tip of the cone, two cones touch each other in the dispersion relation. And then you just concentrated looking at what happens near this tip of the cone and forgot about everything else,
Yeah.
right?
So it's essentially you cut the dispersion relation off above and below the cone and just replace it with an infinite cone.
Okay, right. And then instead of looking at what happens in entire lattice and the Schrödinger operator, you look at Dirac operator that precisely describes what happens with the near the point, and then you perturb this Dirac operator result.
Yes.
Yeah. Okay. Thanks.
I believe the physicists think it's actually quite reasonable. I'll just jot up that operator so at least got it.
No,
That's
don't worry, don't worry.
It's
Okay.
automatic.
This is automatic. How many times you can switch it? And right, and then put it back.
It's gonna be blind then.
So nav is just the gradient, one-dimensional gradient. E is one-dimensional potential. It's a one-dimensional Dirac operator we're looking at, but now we've actually
But V acts on a two-dimensional vector just by
Okay.
multiplying every component
Yeah.
by the same number.
you can stick an identity next to it. Formally, it should
Okay,
be an I2
okay.
there. Yeah.
Mhm.
So it's a one-dimensional Dirac operator. The K has, in some sense, it behaves like a mass. This wave number. And yeah, we're acting on two component spinners, C2 value functions. Okay, the electronic properties that sort of gave rise to this consideration of this operator in the first place mean that we're still interested in actually looking at what happens to this operator near zero energy. So in particular, we're actually interested in trying to find L2 solutions of the zero mode equation, L2 bound states. These actually have a direct relevance in the graphene model. They will give you conduction modes along the waveguide. So L2 confinement in the x direction, you have the wave vector K in the y direction. These are modes that propagate along the waveguide. guide, counting their number, for example, will give you information about how much conduction you can get along the way. So trying to find at least combinations of K and V that will give rise to solutions, in this case is an interesting problem from a conduction point of view. I'll generalize it slightly and basically look at cases where 0 belongs to the spectrum of this operator. So clearly, if you've got eigenvalue, 0 is in the spectrum, but more generally, other things.
If you put V equals 0, then you have a gap of the size K, right?
That's correct.
All right, so you want V is big enough so that you get the 0.
If K is non-zero, you need V to be suitably large to get back inside that gap, that's true. But K will be one of the things we vary. Okay, so the two actual spectral problems will be looking at the same operator, this operator on the board, but varying different things. So the first one, in some sense the more obvious one, is to look at this as a spectral problem relative to K. Okay, so I just define the K spectrum as all of the complex numbers, moving into complex plane, for which 0 belongs to the spectrum of the operator we're looking at. Okay, so certainly we'll pick up all of the 0 modes and other types of spectrum potential. There's another problem that I want to look at, and that's somehow related to the dependence of this problem on V. To make it a spectral problem, I'll fix a particular potential V and then look at scalings of this potential. So I'll stick a scale or a coupling constant, which I'll call gamma, in front of the potential, and then ask the question for which scalings, even in the complex plane, 0 belongs to the spectrum of this operator. So these are the two different spectral problems. The first one, in some sense, is more relevant. If you have a fixed V, you want to know all the different wave numbers that give rise to bound states, and this will tell you something about the conduction. It turns out the second one's a bit easier to answer, so actually I'll spend more time looking at the second spectral problem. It's related to graphene. Mathematically, it seems to, I'm not quite sure it's more interesting, it's just a little easier to study. In both cases, the dependence of the operator on the spectral parameter is linear. So in the first case, we can just peel off the K, it multiplies the third Pauli matrix. In the other case, it's just gamma times V. And then there's a bit that is independent of the spectral parameter in the front. So in both cases, we're looking at linear spectral pencil problems. The things are not self-adjoint. If V is real, that operator is clearly self-adjoint, as is that one, but it's both assigned indefinite, so we're not picking up a self-adjoint problem. In the other case, if K is real, that will be a self-adjoint operator. V is real, as it will be throughout, that's self-adjoint. It may be sign definite or it may not. If it is sign definite, then we are back in the self-adjoint realm. We can say something a bit more. If it's V is sign indefinite, then we're definitely dealing with a non-self-adjoint problem. Okay, I just want to spend a brief moment actually discussing the careful definition of these operators. So first of all, so I want to define this operator that's on the board. First thing to do is define it without V. V equals 0. In that case, it's just a constant coefficient operator. You viewed as multiplication on Fourier space. So there's no problem in defining it as a closed operator. The domain is the ordinary subleft space H1. Got a nice formula for the adjoint. It's not necessarily self-adjoint if K is complex, but there's a nice formula for the adjoint. And we can calculate the usual spectrum. So there's just the spectrum of the operator. It's all the central spectrum. There are two bits to it. They start at plus and minus K and then head off to plus and minus infinity along the real axis. So I'll just try and give some idea of that. So K is actually a real number. We pick up two pieces of the spectrum starting at K and going to plus infinity. K is positive. And from minus K down to minus infinity, and that is exactly the gap picture that you're talking about. If K is off the axis, we can get something that decays down to the real axis in both directions. So it's symmetric under sign inversion. It's going to be something like that. And in the case that K is actually imaginary, that's a somewhat degenerate situation. We end up getting all of the real axis and the bits of the imaginary axis up to and down to minus K. So the picture changes a little bit as we go through different values of K, but we can certainly draw the curves for any given value. In particular, the point 0 is only part of the spectrum if k is an imaginary number. So in all other cases, the operator with 0 potential is actually an isomorphism from H1 to L2. 0. Oh, well, it's an imaginary number. So long as k is not on the imaginary axis. Okay, well that's the unperturbed operator. The potentials that we want to consider, well, basically we want a class of potentials that are relatively compact to the unperturbed operator, to make adding them on rather easy. The class that sort of brings us to is this, what I've denoted as C0 L2, so functions that are locally L2, but decay, at least their L2 averages, decay as we go to infinity. So some condition of that order. And I'll just mention at the moment that other classes, if we put a bit more decay on, if we insist that these L2 averages are LP integrable as we go out to infinity, get a slightly different class that will come back into the discussion in a moment. Okay, so for these potentials, you can show that multiplication by them defines a compact map from H1 to L2, so there's absolutely no problem. So it's relatively compact. Relatively compact perturbation with respect to the original operator, so we can add the two using usual perturbation ideas. So we get a closed operator. The domain is still first Sobolev space, and the adjoint has a nice formula as well. In terms of the usual spectrum, we'll have an essential spectrum that looks exactly like it did before, but we'll pick up potentially isolated eigenvalues for finite multiplicities, which could potentially accumulate to the essential spectrum. So very sort of standard picture. Okay, most of that translates into something for the other spectral problems we're looking at. So we can get a similar sort of picture for these other spectral problems at this broadest level. So we've given the result here for both the K spectrum and the gamma spectrum. All of it is using the basic assumption that we've got a function that's locally L2 and decaying at infinity. For the K spectrum, we pick up the entire imaginary axis as a central spectrum, and then a collection of isolated points, discrete spectrum. So these points live off the imaginary axis. They all have geometric multiplicity 1. They can only accumulate along the imaginary axis. The algebraic multiplicity may not be 1. It may be higher. In the case of the gamma spectrum, it's actually a bit neater. There is no essential spectrum. What we end up with is just a discrete set of values in the complex plane. And all of those points are geometric multiplicity 1 eigenvalues. Algebraic multiplicity, once again, may not be 1. So there's some very general pictures that are quite straightforward. And you can get these quite quickly by turning the spectral problems into usual spectral problems for non-self-adjoint operators. So in the case of the K spectrum, K belongs to the K spectrum if and only if minus K is an element of the ordinary spectrum of this operator here. Sigma 3 times T00, that's actually anti-self-adjoint. Sigma 3 times V will be a relatively compact perturbation. The spectrum is sigma 3 times T00 is the whole of the imaginary axis. So it's the usual business of adding on a relatively compact perturbation. Picking up, the essential spectrum stays the same, you pick up some, potentially some eigenvalues. For the gamma spectrum, it's an inversion, it's a slightly different way of looking at it. We can invert the unperturbed operator, the operator with V equals 0, if we assume K is off the imaginary axis. And then what we've got there is actually a compact operator. So this maps from L2 up to H1, then back down to L2. That's relative, well, it's compact from H1 to L2, so overall that's a compact operator. So we really want the inverse, the reciprocals of the spectrum of a compact operator. It's not self-adjoint, but that's not a problem. The geometric multiplicity, the bound on that, or the fact that it can only be 1, that just comes directly from the fact we're working with an ODE. A very straightforward calculation. Okay, the Dirac operator has plenty of symmetries. Conjugate with the other Pauli matrices. We can conjugate, take a complex conjugate. All of these things obviously have symmetries, descend to symmetries in the spectra. So for the case of the K spectrum, it's the same, well, it's in both the real and imaginary axis, it's reflective, reflection symmetric. And it doesn't matter whether we take plus V or minus V, we get the same spectrum as well. So this spectrum is really, it's got quite a few symmetries, and in some sense we only really need to bother looking in the top right quadrant. For the gamma spectrum, it's certainly, the sign is, it's symmetric under sign inversion. Need to be a little bit more careful when we come to how it behaves under K. I haven't actually written K in the notation usually. I'm going to fix it in a moment. But if we do include the K in the notation, if we change the sign of K, we get the same spectrum. And if we want to take the conjugate of the spectrum, well, we need to actually take the conjugate of K. So for real K at least, it's, the spectrum will be symmetric in both the real and imaginary axes. Just a quick note on the values of K that we haven't really included in this discussion of the gamma spectrum. That's the imaginary axis. In some sense, K is a wave number. We're interested in real values of K, so the only one that crops up as a problem is K equals 0. In that case, we can actually solve the eigenvalue equation, or this ODE, explicitly. And what we find out as well, if you take any potential that decays at least so that it's integrable, we end up getting the whole of the complex plane as our spectrum. So that's a relatively boring case. Well, it's a degenerate case that we won't consider further. So from now on, at least for the gamma spectrum, I'm going to focus on the case of real positive decay. Okay, well the first thing is the case where we do actually really have a self-adjoint problem. So a slightly more symmetric version of the compact operator I came up with before, we can actually split the potential around the inverse of the unperturbed operator, a square roots of mod V, and we can shift the sign out to the front. If our potential is single sign, then this is just plus or minus 1. So what we've then got is a self-adjoint operator. So we're really looking, so for at least for sign definite potentials, we really do have a self-adjoint problem. Obviously, the immediate consequence is the gamma spectrum in that case is a subset of the real line. As soon as our potential has variation in sign, this will become some unitary. It won't commute with the rest there necessarily. In general, it won't. So we will pick up a properly non-self-adjoint problem. And complex eigenvalues certainly exist. It's very easy to construct numerical examples where these things pop up. Basically, any operator that's not sign without a sign definite V will produce complex eigenvalues, maybe with a bit of a tweak, but they're not hard to construct. Okay, in fact, we can do somewhat better if we take a potential that's anti-symmetric, an odd function, then we can actually show that the gamma spectrum is entirely separate from the real line. It's an argument based on symmetries. It's not particularly difficult. So it's a very sharp contrast. Instead of being entirely on the real line, if we take something, an anti-symmetric potential, obviously that's very sign indefinite, but the spectrum has shifted entirely off the real axis. Okay, the next sort of thing we attempted to do is get some idea of the distribution of points inside the spectrum, how they scattered in the complex plane. They can't accumulate anywhere except at infinity. So the obvious sort of thing to look at is how many, a counting function based on radius, how many points in the gamma spectrum inside a disk of radius r. Okay, in that context we can certainly get bounds. So to get bounds we need to impose a bit more decay on the potential. So we need to assume local L2 again, but those L2 averages decay, or if we integrate the Pth powers, they'll decay. So in that case, and then this applies to any P greater than or equal to 1 finite. In that case, we can get a bound on the number of points in the gamma spectrum inside a disk of radius r that grows as r to the power p. The LP normally, the potential, and then some constant. So the constant depends on p, and the explicit value of the constant that we got for p equals 1 is there.
Does this include algebraic multiplicities?
Yes. Okay, a brief comment on the proof. Sweetel's bounds work for the case where p is strictly larger than 1. With a bit of effort we can like the image ring and then Sweetel's bound. So that will work when p is bigger than 1. When p is equal to 1, it's a rather different argument. I'll just back up to the previous slide. So this idea here, rephrasing the spectrum, for a sign indefinite potential, this is going to be a unitary here, but if we then look at the singular values of this operator, we're basically going to look at the moduli of the eigenvalues of just that bit on the right, which is the operator corresponding to the potential mod v rather than v. So moving from potential v to mod v, we pick up a sign definite potential. We go from eigenvalues to singular values. So we can use Weyl's inequality to get estimates on the eigenvalues for the original v from the eigenvalues for this sign definite potential, and then there's some other arguments we can use for sign definite potential to bound the number of eigenvalues. So ultimately, that's how we get the p equals 1 case. Okay, and I'm not saying these are the only ways to do these arguments. Okay, so those are upper bounds on the distribution of eigenvalues. We can get some lower bounds as well. So I'll restrict attention to trying to find out how many eigenvalues lie on the real line. So in that case, we'll work with potentials that are L1 globally, L2 locally. And then it's possible to show that the number of eigenvalues from 0 up to some positive point on the real line, some r, is bounded below by the modulus of the integral, growing linearly in r, and then a lower order remainder term. Okay, and the symmetry immediately implies a similar estimate holds on the negative real line, as will all of these estimates will have the corresponding version for the negative.
Is the class L1 of L2 is different from L2 globally?
Sorry?
Is it a different class than just a global L2?
I'm not sure. My expectation is that yes, you would get more eigenvalues. I mean, the upper bound would grow as R2 in that case. We haven't spent much time trying to construct potentials where you do actually get more, but I would assume that you could find more. Okay, well, in particular, if this integral is non-zero, we pick up infinitely many points on the real axis. There will be infinitely many points in the complex plane as soon as the potential is non-trivial. If that integral of the potential is non-zero, then infinitely many points will actually be on the real axis. In some physical sense, they're like the more interesting ones. There's a limit to how much we can improve these lower bounds, of course, for the eigenvalues on the real line. For example, these anti-symmetric potentials have no eigenvalues on the real line. Obviously, in that case, the integral is 0, but there's a clear limit to how much we can improve that lower bound. Okay, so far we've got upper bounds and lower bounds. If we work with these globally L1 type potentials, if we look at counting the number of eigenvalues up to R on the real axis, got an upper bound of the form R times the L1 norm, constant divided by pi. Asymptotically, the best constant we can get is for all potentials is C equals E. We've also got a lower bound, which is the modulus of the integral. Okay, so the question is, can we make those match up? Is it possible to actually get the asymptotics for the number of eigenvalues? Which one of those is it likely to be? Well, there's certainly one case where there's a good chance of getting something, and that is where those two numbers actually agree, modulo that constant stuck out the front. So if we take a sign definite potential, the L1 norm is the same as the modulus of the integral. So at least in those cases, there's a reasonable chance of getting asymptotics, and we know what we a pretty good idea of what the asymptotic should be. There's another class of potentials I want to introduce which allow the same asymptotics to be obtained. So these are quite a bit more restricted. I want to look at the class of potentials that have bounded variation and compact support. So certainly piecewise first differentiable, continuously differentiable functions, finite number of pieces, compact support. Such potentials are going to be in this class. And all of the examples that we've dealt with numerically are piecewise constant, so they all fall inside this class. Okay, and there's one extra condition I need to impose on such potentials, and that's a gap condition. So intuitively, a gap is a fairly obvious thing. It's an interval inside the support that's not part of the support. So we have some bit of the potential here, some bit there, and there's a bit where it's equal to 0 in the middle. In other words, if you take the convex hull of the essential support of the potential, that includes bits where the potential is 0, a Lebesgue measurable part of that. Okay, so to have no gaps means that can't happen. Okay, so for asymptotics, we can get them in two different cases. For single sign potentials, that's perhaps not so surprising. And then in the second case, when the potential is one of these potentials, bounded variation with no gaps. So in those cases, the asymptotics is, well, I guess what you'd expect from the bounds that we've got so far. We need to take the modulus, the integral of v, and then it gives a linear term, the asymptotics multiplied, you divide by pi. Obviously, the same asymptotics apply on the negative. Okay, so that's a reasonable, well, it's not a surprising result in some sense, but we can at least get that out in those cases. And of course, you can translate estimates for the asymptotics of the counting function into asymptotics of the eigenvalues themselves. So if you're interested in the eigenvalues on the real axis, enumerate the positive ones, then gamma n is going to be pi over the L1 norm times n, also in the correction. Okay, in the case of single sign potentials, that's all of the eigenvalues. In the case of these bounded variation no gap potentials, that may not be all of the eigenvalues. There may be complex ones if the sign varies. It's only in the sign definite case we're sure that we've got more.
So that formula is also sign definite case, right? Otherwise it's not L1 or...
Oh, yes, you're quite right. Otherwise it needs to be the modulus of the integral. Yes, sorry. Yeah, it was copied from something else. Okay, well, what about pushing on from that? So, sign definite, no problem. Bounded variation, with at least no gaps, that's not a problem. What about introducing a potential with one gap? So I want to take a potential, well, a sum of two potentials. So V1 and V2 are each bounded variation, no gaps, and I want to put them apart. So there's a bit in between where the potential is 0. So the disjoint support. Okay, so these will be my one gap potentials. Okay, if the integral of the potential is 0, it follows that the real axis can only contain finitely many points in the gamma spectrum. So that's still very much in line with what we got. We'd expect asymptotics, the leading coefficient would be the integral. That would be multiplied by r. We've got a finite number, so we're already down in the remainder term. Okay, so now let's deal with the case where that's not, the integral is not 0. So I need to introduce a little bit of notation. The supports of the two pieces, I'll use AJ up to BJ as the two supports. I'll put V1 to the left of V2. It's the same as saying V1 is less than A2, right end of the support of V1 is left of the left end of V2. And I'm assuming now that the integral is non-zero. So these little v's are just the integrals of the two pieces. Okay, a couple of other things I want to introduce. So two more numbers. Alpha, in some sense, measures the gap length. So A2 minus B1 is the gap length, multiplied by this positive wave number, and then take the hyperbolic tangent. So we get a number between 0 and 1 that measures the gap. As we go to 0, the gap closes up. As we go to 1, the gap becomes a gap. The beta is a nice ratio of these integrals of the two components of V, and it measures the relative size of these two integrals. So beta equals 0 means they have exactly the same size. As we go up through, well, beta equals 1 means they have actually opposite signs, same size but opposite signs. Oh, sorry, no, it means one of them is equal to 0. One of these integrals actually is 0. If they have the same sign, then we're in 0, 1, and if they have opposite signs, beta is strictly larger than 1. So beta is giving some measure of the relative sizes of these two integrals. Okay, so there are two numbers. Now, unfortunately, I'm going to have to introduce a few other auxiliary functions. So the first one, well, when alpha beta is larger than 1, we can define this thing. It's explicit, possibly not in a way that small children should be introduced to. I'll say a little bit more about exactly what sort of variation is going on there in a moment, but at least it's an explicit formula involving alpha and beta. Now, when beta is actually a rational number, we need to do even a little bit more. When beta is rational, we can write it P over Q, assume P and Q are co-prime. I need to be a little bit more careful. If both P and Q are odd, then that's how I'll stay. So just P beta and Q beta are just the numerator and denominator of the reduced fraction. If P and Q have opposite parity, I'll actually need to multiply both of these by 2. Okay, so there's a bit of a twist, depending exactly the form of the quotient for beta in this fraction. Okay.
Sorry, P and Q are what?
Natural numbers.
Just arbitrary numbers.
Yeah.
Be the
Well,
rational. Okay.
Reduced form, co-prime, so reduced form of the fraction. Okay, and now I want to define a coefficient. If alpha beta is less than 1, it's simple, it's just 1. If alpha beta is larger than 1, we want to use this formula here, at least when b is irrational. And if alpha beta is larger than 1 and b is rational, we want to go even a bit more complicated. So the new alpha beta stays inside, and then we need to take the p and the q, bits coming from the rational expression, and then we've got the floor as well. So that's the largest integer strictly less than the thing inside it. Okay, it's not a particularly neat formula, but it's...
Sorry, is it obvious that the limit when alpha beta goes from larger 1 to smaller than 1 is, I mean, whether it is continuous, or when alpha beta goes from larger than 1 to smaller than 1? Or is it not?
There is continuity of that bit, as you
Yeah,
come across
yeah,
that.
yeah. So
That
that
one
I'm
is yes.
interested in, yes.
This one is not necessarily continuous, obviously, because it's got jumps in it. But I'll say a little bit more in a second about what we can say about the continuity of this thing.
But new alpha beta is continuous when you cross 1, yeah.
That one's okay. Well, it has an appropriately defined limit. Okay, so these are the preliminaries, and it's this one, ultimately, that I want. Okay, so the statement of the result. We've got a potential V that's a one-gap potential. The V1, the V2, the alpha, the beta, all of these things are as I introduced them over the previous page. Okay, we're assuming that the integral is non-zero. I've already dealt with the case where it's equal to 0. I'm also going to suppose that alpha beta is not equal to 1. That's a transition, and it's actually quite hard to deal with the transition cases. In the case that alpha beta is larger than 1 and b is rational, I'll need to make one further assumption. And that's basically the assumption that the bit that appeared inside the floor function is not sitting on an integer. So those are, again, transition points. So the thing goes not back. So yeah, we need to make the assumption that we're not actually integer valued inside there. Okay, so under all of those conditions, we can get the asymptotics for the number of the counting function, the number of eigenvalues. So the number of eigenvalues up to r grows linearly in r, and the coefficient, well, the 1 over pi that's followed us throughout, this parameter, or this coefficient that I defined over the page, multiplied by, that's the integral of the potential, the integral of v. So this coefficient stuck out the front is a modification of the asymptotics from just plain ordinary integral asymptotics. Okay.
Is there some renewal theorem hidden somewhere here?
Might be hidden.
Well, I mean, this having slightly different behavior for things being rational and irrational, is it?
I'll come on to how it comes up in this work in a moment, but essentially it comes up from counting zeros of either a periodic or a quasi-periodic function. And it's a fairly direct sort of thing ultimately. It may well have some sort of link. Okay, to try and get a slightly better handle on what's actually going on here. So if we fix beta, so that means fix the relative size of the two potentials. And what I want to do is vary the separation between them, stretch the gap. Okay, so that means change alpha. Okay, so alpha goes from 0 when there is no gap, and then it rises until it gets to beta. If beta is larger than 1 over beta. And all the time it's going up to 1 over beta, this thing here is equal to 1. So we're picking up the asymptotic that we would get without any gap. It's just the integral. Okay, then we get to 1 over beta, and we start moving up to an infinite gap, which corresponds to alpha equals 1. And at that point, this thing kicks off. Now, if it's just the new alpha beta, then it goes from the value of 1 here to the value, well, when you multiply it out by that, it gives you this sum of the moduli of the potentials when we have an infinite gap. So this is not quite the L1 norm. It would be the L1 norm if each piece were sign definite, but the V1 and the V2 are actually integral, so if there's variation within a piece, you're not taking the L1 norm of that piece, but you're taking the sum of the moduli of the integrals of the two pieces. So we are transitioning between the two sorts of asymptotics we could, well, might think about getting. So we start with the straight integral of the potential, and we transition towards something that looks more like the L1 norm, at least for the two chunks. Okay, so that's when beta is irrational, so we just multiply by that coefficient. And that transition is continuous and it's monotonic. So that's it's not necessarily so surprising. But then in the rational case, we impose upon that this extra bit with the floor function and the p and the q coming from the rational expression for beta. Now you can show that that coefficient a alpha beta has bounds above and below in terms of mu. And the bounds, well, minus 2 over q beta plus 2 over q beta. So when the rational expression becomes bigger, when the denominator becomes bigger, that gets tighter to the actual irrational case. So in some sense what we've got is a so if we take alpha along there and the coefficient up here, well, without the what's multiplying the integral, goes along to 1 until 1 over beta, and then it takes off. This will be the new curve. And then in the rational case, that will be approximated by some sort of step function, which may or may not actually get to 1 at the end. It could peter out before 1. Even the gap case could actually not have the asymptotic value. And these pieces get smaller and a better approximation as the rational number becomes more irrational in the sense of the denominator increasing. Okay, so at least for the asymptotics of the counting function, hopefully we persuade you that's a relatively subtle behavior relating to the size of the two potentials. So we're only varying the gap, and it's just the size of these two pieces of the potential that determine a fairly complicated behavior of the leading order coefficient. And we go back to actually looking at the asymptotics. So all of these asymptotics are in the form of a constant times r over pi. And this constant, well, in some cases it's the integral of v, in other cases it's starting to approach the L1 norm of v. And using the previous result, we can actually show that you can get anything strictly between those two. So if you take a little u, that's going to be our L1 norm, a little v, that would be the integral of the potential, and take any constant between those, you can find a piecewise constant one-gap potential that has this for the asymptotics, and the constant c is just given by a. So you can get any type of behavior on the spectrum for a given potential. And if you actually want to push it out with the equalities in any of these places, you can certainly do it. Not clear that you can do it with one gap potential, but for a symmetric two-gap potential, we can prove that you can pick up all of the equalities as well. So you can actually get any coefficient between those two extremes. Okay, just give some brief information about the methods. A little bit of time talking about this, a little bit more on the decay spectrum. As I said, most of the methods are very much classical in spirit. The eigenvalue equation is just be viewed as an ordinary differential equation on the real line. At least when we're dealing with real gamma, we can assume the function psi is real valued. We can introduce what's known as the Prüfer angle, so basically write the two components of psi as a complex number. Theta will then be the argument of that complex number. And you can get a very nice equation for that Prüfer angle. So it's a non-linear equation, but it's about the nicest sort of first order non-linear equation you can come up with. Potential appears very nicely, k is the wave number, and then cos of 2 theta. There's all sorts of classical theory of the existence, uniqueness, dependence on the parameters of these solutions. For the solutions we're interested in, well, we can actually work with any L1 potential, and you could probably get through the rest of the analysis with arbitrary L1, not locally L2 functions if you move to consideration of forms rather than directly with the operators. We haven't gone through that. You can prove that for any V in L1, the limits of this theta at plus and minus infinity exist. And furthermore, there is actually a unique solution, or two different solutions potentially, that have prescribed limits at plus and minus infinity. So the limit we're most interested in at plus infinity is minus pi over 4, and at minus infinity is plus pi over 4. And the reason we're interested in those limits, they correspond precisely to the solutions of the original problem that are in L2. So we get two solutions at plus and minus infinity. One will decay exponentially, one grows exponentially, and obviously to get L2, we need the one that decays exponentially. So in order to find a point in the spectrum, well, we need to match the one that decays at minus infinity with the one that decays at plus infinity. So we need to match these two different solutions. The matching condition, well, you can express it relatively nicely in terms of this function, which in some sense just measures the difference in the proof angles at 0 for the two solutions that we want. That difference needs to be a multiple of pi. I've added in the values of plus and minus infinity. So the condition we ultimately get is that this function delta should be an odd half integral multiple of pi. So we get an entirely equivalent condition for a point lying on the real line in the gamma spectrum in terms of this lovely continuous differential, in fact arbitrarily differentiable function delta. And there's a string of properties that delta has that are relatively straightforward to obtain. Well, the first one's very easy, value at 0 is 0. We can get a uniform bound on the growth of delta with respect to gamma. It grows, well actually we can do slightly better than that, but twice the L1 norm times the linear factor. We can get asymptotics for it. So for any potential, any L1 function V, the asymptotics for the large gamma is governed by the integral of V, which is ultimately where that coefficient turns up from. And for an arbitrary potential, the best we can really do there is a little o of gamma. The single sign potentials, that also translates into a nice property for this delta. That translates into monotonicity. So if V is positive, it's monotonically increasing. If V is negative, it's monotonically decreasing. And of course, that means it's very easy to then count the number of points, the number of eigenvalues. The number of crossings that we get here is going to be determined entirely by this asymptotic term up to a lower order corrections. So for single sign potentials, that's very much how the asymptotics are obtained. In the case of no gaps, a little bit more work needs doing. We need to improve this formula here a bit. So we get the same asymptotic, so just move that term onto the other side, except we need to clean up this term here. So in particular, we need to go little o1, but then we need similar expressions for the first derivative in order to retain monotonicity, at least for large gamma. And in fact, to deal with the one gap situation, we need to push on a little bit further and deal with the second derivatives as well. So it's a little bit technical, but relatively straightforward. We can get those little o1 estimates there. And this really does need the bounded variation. You need to estimate the decay of some oscillating integrals. So you need some extra regularity on the V.
So in particular, you're saying that the delta grows as gamma plus a decaying term. It is not even O of 1, it is O small of 1.
That's correct, yes. This is not true for an arbitrary potential in L1. This does rely on the thing having compact support and being relatively regular.
Is it easy to see from the proof equation?
Or
Maybe not all the details, but
I mean,
yes,
essentially,
from this equation.
if you just integrate,
Yeah.
okay, you get the difference of theta on that side, you get the obvious leading order term coming out of the integral of that. And then you need to
the
integrate
next
this
one
thing.
decays because you integrated the oscillations
Yeah.
with stationary phase, something.
Yeah, yeah, that's
Okay.
exactly it.
Right.
So it's, yeah, this one's gonna, it's an oscillatory phase, exactly. Okay, so for the one gap result, the key step, well, key first step is to turn it into something that just involves counting zeros of a relatively same function. So we can work out the change in the proof angle across each piece of the potential. That's basically the previous formula. And we can get asymptotics of this. Okay, this is the one for across the whole of the real line, but you can get a very similar formula just across V1 and across V2 from left to right. And the gap in the middle, that's just, that's where V equals 0. You can write down the solutions of the differential equation explicitly, so you can propagate the proof angle across that gap without a problem. And you can put all that together, and what you then get, this condition that lambda, a real number lambda is in the spectrum, comes down to gamma being a 0 of a function that's very closely related to this. Well, the x here is actually just the scale of gamma. It's mod v1 plus v2 times gamma, something like that. So we turn using the proof argument, we turn the problem of finding the real eigenvalues into counting the zeros of this periodic or quasi-periodic function plus a perturbation. So the perturbation, crucially, has all of those nice estimates. It decays, its first derivative decays, and its second derivative decays. So those decays come directly from these estimates here. Okay, so there's a little bit of work, not too difficult, but we ultimately need to consider such functions and count their zeros. Okay, and there's a result that is exactly, well, you can see the same coefficient appears in that result, obviously feeds back into the spectral asymptotics. So the number of zeros of this function here, if phi satisfies these decay estimates, is given entirely in terms of these parameters alpha and beta, and clearly beta now splits the case periodic versus quasi-periodic. So some difference in behaviour is perhaps a bit more expected in this picture. So counting the zeros of, well, at least without the phi on the end, there's some results that go back at least as far as the 30s, P. Stein. In the irrational case, they got the result without the phi. In the irrational case, without the phi. In the rational case, they considered a slightly different problem. There was an extra phase in there, and they integrated across the different phases, so got an average result. We didn't actually manage to find this result in the form that we needed it anywhere in the literature. We did spend a little while looking, couldn't actually find it, so we went and proved it ourselves. The proof is not particularly difficult, it's a little bit long in places, but essentially what you do is deal with the case when phi equals 0, and then treat phi as a perturbation and show that things don't change by more than the error term.
Can you actually get O small of r by introducing phi, or are you getting something better?
How big could the error be?
How big could the error be? Yes.
The estimates that we've got are only O small of r.
So you don't think you could do better by?
Depends on the case.
Yeah.
I think you would struggle in the beta irrational case. That's actually the harder one for the perturbation. It's easier for the leading order.
Because you could have many sort of zeros that are easily destroyed, or
Yeah.
you introduce
Well,
one
this-
of the ideas.
Give you a brief overview of some of the ideas in that. So the leading order case, phi equals 0. When alpha beta is less than 1, that's the easy case. The extra bit, the alpha cos beta, is just a perturbation. I mean, alpha beta less than 1 is saying that the gradient of that thing is bounded by, well, it's less than 1. So that one's relatively straightforward. When alpha beta is larger than 1, the quantity that we want, well, we can break it up into pieces. So we need to show this limit is equal to a alpha beta times 2 pi. So what we need to do is basically count the number of zeros of our function on each interval of length 2 pi, or in fact each interval of length pi, and add them all up. If we go up n intervals of length 2 pi, take the limit as n goes to infinity, we should get this. It looks like there's a missing 1 over n on this side. Yeah, it should be a 1 over n there. We need to average across these intervals. The function, well, this m function just measures the number of zeros in the interval that we're looking at, and it can be re-expressed with a little bit of work in terms of the value of some characteristic function on intervals and then translated. So this is the characteristic function on the interval j. That's the interval j there. That's an interval and that's an offset. It's a scale. And then we just take periodic, well, translates by 2 pi and add them up. So in particular, this thing is a periodic function with period 2 pi. Piecewise constant. When beta is irrational, then we can use ergodicity. It's essentially Weyl equidistribution. These multiples of beta will then uniformly distribute. Well, once we move them back inside the interval 0 to 2 pi, they'll be uniformly distributed. This sum will become an integral, and then we just need to know the size of the interval j here, and we can work that out. And that's where we get this lovely, well, we can see that the new alpha betas already emerged in that form. In the periodic case, it's a pain in the arse. The limit, well, periodicity means the limit can be worked out by just adding up the appropriate number of these quantities here. And then it's a bit tedious to go through and actually get the formula, but it's a direct calculation. So that's the case phi equals 0. You then need to add on the perturbation, and actually then it flips around. The rational case is a lot easier than the irrational case. In the rational case, this extra condition that we imposed means that the zeros of f0 and phi equals 0, they're all transversal. There's no touching zeros. In fact, this being 4 times an integer is exactly equivalent to having touching zeros. So long as you avoid touching zeros, all the zeros are transversal. It's periodic, so this is a uniform condition. And then imposing this extra condition on phi, we only need it for n equals 0 and 1. The values of phi and the values of the first derivative. It won't perturb the number of zeros for sufficiently large x. So in that case, actually, the error will be big O1. In the irrational case, you will have to consider turning points of the function that are arbitrarily small. So there might not be zeros in f0, but if they're coming close to the axis, you're going to have to look at them. And it's not entirely clear how many of these there are. The small here, because we're only imposing little o1 conditions on the phi, the small needs to basically go down at the same rate as that little o1 condition. So the number of such turning points is little o of r, but as far as I can tell, you're not going to do much better than that unless you impose stronger decay conditions on the phis. I mean, the number of such turning points should be somehow uniformly distributed as you go out to infinity. And it's only the fact that the small actually gets smaller as x gets bigger because of the conditions on phi that means they get further apart. Okay, so you need to show that the number is actually little OR of such turning points. And then for sufficiently large x at least, the changes at each one of those turning points to the counting function can be bounded by 2. And essentially that comes from the fact that we can get a uniform bound on the sum of the moduli of the first 2 derivatives. So these turning points, the small turning points, the first 2 terms are actually going to be small, but we're rescued by the second derivative, which in those cases we can show has to be bounded uniformly away from 0. So then the perturbation can't screw up our zeros by more than 2. The turning point could go across or could be pulled back, but it's only changed by 2. I suspect I'll probably run up my time, haven't I?
I think you can just get on.
Okay, I mean the results for the K spectrum are quite a bit shorter, so there's only a couple of slides and the results are considerably less detailed in some sense. For the K spectrum, so this is where we're going to fix V and just look at when K equals 0 gives us a non-invertible, non-boundedly invertible operator. So when K, for which values of K we have a non-boundedly invertible operator. The anti-symmetric result goes through, so if we have an anti-symmetric potential, the discrete points in this spectrum, remember we've got the entire imaginary axis and some discrete points lying around, those discrete points can't fall on the real axis. So that bit goes over just as before. Single sign potentials don't have a special role. They don't give rise to a self-adjoint problem. So there's not a lot we can really say about those in particular. There's another class of potentials that we can say something about. On the other hand, for the K spectrum, we have boundedness. So for the gamma spectrum, we had arbitrarily large points in the gamma spectrum. We were trying to count the number inside big disks. In this case, we've got bounds on where those things lie. So none of these results are, I think, optimal. I mean, they can certainly be improved, but they're sort of more representative of the kind of bounds that you can get. If you want to get bounds on the real part of eigenvalues, discrete eigenvalues of the K spectrum, that's a very straightforward thing to do. The L infinity norm of V, for example, provides such bounds. And you can also bound the imaginary parts of the eigenvalues, so the moduli. This gets a bit more tricky. You need a little bit more information about the potential. The version I've got there is for these compactly supported potentials of bounded variation, and the variation enters. I believe you can get both of these bounds for pretty much arbitrary L1 potentials. In this second case in particular, you're going to need some more information about the potential, something like the decay rate in the Riemann-Lebedecker lemma. It's going to involve something else to get tight bounds on how far up the imaginary axis you can go before you don't have anything creeping off the imaginary axis into the spectrum. Okay, but I'm pretty sure those will extend. In terms of scaling with V, this one scales linearly in V. This estimate scales as the square. So if you put a gamma in front of V, it goes as gamma squared. The linear scaling is, you can't do better than that. As you scale V, the eigenvalues will grow linearly at least. It's unclear, whether this quadratic scaling is necessary. I'm strongly suspicious it's not. But in some sense, if you go up the imaginary axis, there's no particular reason you can't have an eigenvalue just coming off very slightly. It's near the essential spectrum, so it doesn't violate any of those ideas, but I'm pretty sure that's more an artifact of the method. I think that should be a linear bound as well. In terms of counting the number, okay, it's going to be, well, actually, it's not clear it's even going to be finite. So the results here, again, looking at potentials, compact support and bounded variation. The total number of points the total number of discrete points in this K spectrum. If you're only interested in the real ones, then you can get a bound that grows linearly in V, like the L infinity norm here. The I is the support of the potential, so measuring the size of that comes into the bound as well. And if you want to know about all of the points in the discrete spectrum, so all the complex ones as well, the bound again gets a little bit more complicated and involves extra information about the potential, something like the variation. Once again, the scalings, in terms of V, that one's got to be optimal, that one probably isn't. A linear scale is more what you would expect. In terms of the method, this business about having compact support is crucial to all of the basic arguments that we've got at the moment. Most of them use something like a Weil-Titchmarsh type of function, and that needs to be extended to an entire function of exponential type. The only way you can do that is for a compact potential, or potentially a potential that has super exponential decay. So some very rapidly decaying potentials will be possible. Whether these results hold for arbitrary L1 potentials, this is unclear. It's not clear that we even get a finite number of points in the K spectrum at this point. So for certain potentials that have infinite range, it's not actually clear at the moment how many points are in the K spectrum. You can get, for more arbitrary potentials, you can certainly get bounds on the number of points in the spectrum away from the imaginary axis. In particular, if you start a little way up the real axis and go off to infinity, you can get a finite number in there. Okay, well, it's clearly going to be finite. Unfortunately, these bounds, obviously, they grow as epsilon approaches zero. So you can't, it seems a bit tricky. I mean, we're moving into the essential spectrum, so getting the bounds is going to be harder. Except for one particular class of potentials, which turned out to be sort of an odd one in this case. So the potentials that we can deal with, what are called central potentials, which one dimension is possible, higher dimensions, I guess it's a slightly different definition. So what I want to think about here is a potential that decays from a central point. So we've got some x naught where the potential reaches a maximum, and then we have decay away from that point. If we impose an L1 condition, that means the potential has to have one. In this case, has to be a positive potential. Obviously, we can deal with negative potentials. The spectrum is the same. Okay, so one bump potentials somehow decay, but they can go to infinity. There's no bound, there's no condition on bounded support. So for these potentials, we can work out exactly how many points belong in the K spectrum and sit on the real line. And it's an exact quantity. It grows linearly as we'd expect. It's given by the floor function. So we just need to work out the integral of V and scale it suitably and work out the nearest integer to within a half. So in this case, we get a very precise answer.
Because you actually built the eigenfunctions explicitly?
No, it's a monotonicity argument. So we can go back to the proofer angle and show that that varies monotonically in K as we go away from K equals 0 up to K equals to infinity. So yeah, we just simply need to know the values of each endpoint and get the rest. So yeah, getting the monotonicity of the proofer argument, that delta function, doesn't appear to be that easy. Well, it's possible, but it's a bit technical. There is actually a bound, Calogera's bound, for Schrödinger operators, which at least formally looks quite similar. It's more or less the CLR for one-dimensional Schrödinger operators, where the potential is one of these sorts of things, a central potential in this sense. I mean, the form of the actual bound is for three-dimensional operators with rotation and symmetric potentials, which decay from a center point. But the actual hard work is the one-dimensional problem. So there is a very similar sort of result, at least in a formal sense. The proofs, well, they're not that close, and that uses the Riccati equations and other things, but at least it has a moral cousin out there. My guess is that in this case there are no non-real points in the spectrum. I haven't been able to prove that. I've got some ideas, but the proofer arguments that I've applied to get this don't really work for non-real. And in this case, well, there's lots more work to do. It's not actually gaps that seem to be the issue, it's dips. So if you have a potential of this form, it's a bump potential that has no dips. But if you take two bump potentials with a dip in between, then things change quite dramatically. So we've just done numerical examples, just take two-step pieces. Okay, you can make it 0 in between, you can make it something non-zero, it doesn't actually make any difference. And if you look at the number of eigenvalues that you pick up, you can write down explicit formulae, trig functions, or hyperbolic trig functions, look at the number of zeros of these things in the complex plane, tells you how many eigenvalues you've got. And actually, they grow. The number grows linearly in the gap length. So we're not changing the integral of the potential, we're simply moving two bits apart. And the number of eigenvalues increases linearly in that way. However, these eigenvalues are complex. The number of real eigenvalues appears to remain bounded. So I think there might be some possibility of getting L1 type bounds on the number of real eigenvalues for more complicated potentials. Not clear how to do it, but certainly no chance of getting straight L1 bounds for the total number. And you can see in the previous bounds here, these lengths of the intervals here, something like that has to be there, because the L1 norm of these is not changing as we move those two pieces apart, but the number of total number of eigenvalues is clearly growing linearly in something, so you don't have to have something like the length of the overall support. Okay, I've run out my time fairly thoroughly. Thank you very much for your attention.
Thank you. Questions? Coming back to this phi thing, quasi-periodic plus phi. How much of extra control could you have on phi? Could you, for example, tell that phi actually goes to 0 with some prescribed rate or some rate, and then plus something smaller than
Okay, so the phi comes from these sort of estimates here. Well, phi is more or less this quantity. In order to do better, you're going to have to do better with this result. To do better with this result, you need more regularity on the potential. So bounded variation, I don't think you're going to do much better.
Okay, but for something better than that.
If you assume a couple of derivatives, then yes.
But then you possibly, I guess, might be able to get second term for some. I mean, if you just there could be some ergodic argument, basically, that also counts the number of turning points that come to 0 with prescribed, that are close to 0 with prescribed rate. And basically, each turning point within phi gives you 2 extra zeros, right?
You don't
or,
know.
or
You need
this,
to,
yeah.
you need to balance the number. It may or may not.
Yeah,
But,
yeah, but
Um,
I think that might be, I think having second term might be fun if this.
Yeah, we've got plenty of other things to get on with the complex, trying to get some more asymptotic information about the complex eigenvalues. Is,
I'm not quite sure what you mean, because forget 5. Can you get the second term?
Even for with 5 equals 0,
Well, but my point is that second term might be coming not from phi equals, from the unperturbed situation,
It's
but
already,
it might be coming from the perturbation.
in the unperturbed situation, you already have O small of r. This is it.
So you mean you cannot beat O small of r in the unperturbed?
You see, look at the formula here. You have O small of r.
it's going to come down to what you can do with this.
Can you improve this ergodicity thing? And I don't think you can. I mean, maybe you will have to assume some
Some Dirac-Fontane conditions on
Dirac-Fontane
meat.
properties. Yeah, and then
Okay, I'm happy to assume some Dirac-Fontane properties.
I'm not sure though that even with that you can improve that. I mean, this is you know the lattices they do not take prisoners.
Well, fair enough.
I guess I mean, it's the ergodicity. This thing's got steps on it. It's piecewise constant, but it's got steps. So you are going to pick up basically the worst. You'll need the best estimate you can from the ergodicity result there.
But,
Translate
You know, we will have plenty of ergodic people in this program, so we could ask them, and I'm sure some of them would know.
Ask Jens. Jens will know that.
yes.
Okay, we need to go.
Okay, right, yeah, so let's, if you have further questions, maybe let's ask them on our way back to the institute. Right, thank you very much.